Dear students, we discussed the torque and angular momentum of a particle in the previous classes and also discussed the angular momentum of a sliding block. And today, as a continuation of that one, we discuss the torque on a sliding block. Okay, here the question is this one. A small block of mass m is sliding in the x direction with velocity vi. You can see in this picture a small block of mass m is sliding along this x direction with a velocity v. This v is the vector v, that is, it is moving along x direction, therefore vi cap. Calculate the torque acting on the block about the origin B. Here we have to calculate the torque acting on this mass m about this point, about the point B. Okay, this example is an illustration of the relation tau is equal to dl by dt. We verify this relation in this example. That is, first we have to calculate the angular momentum, then torque we will calculate in the two different ways. The first one is after calculating angular momentum, dl by dt, you can calculate tau. Another method is tau is equal to r cross f. Okay, what we will do is, I will explain once again. We will calculate the angular momentum first, then we can take the time derivative of the angular momentum, we will get a torque. Then we will calculate the force acting on the block, and taking the r cross f, we will find out the torque. And let us examine whether these two torques are the same or not. Fine. Now let us begin. The angular momentum of the block about the origin B, okay, that is denoted by LB, it's a vector quantity, R cross B, that is RB cross B. You know the RB. The bold letter in the Kepler textbook is a vector quantity. Here the RB is the position vector of the mass m from the point B. P is the momentum, that is m into v, therefore I can write this is a RB cross m v. If I take m outside, then this is RB cross v. Fine. This m RB cross v is nothing but RVB sine theta. M RBV sine theta. This is the magnitude only, but the angular momentum is a vector quantity that has a direction also. How to find out the direction? That is very simple. Take the cross product of r cross v. If you look at this picture, if I can extend our RB like this, and the velocity is along this direction, then the angle between, if I take this is the angle theta, this will also be angle theta. Now r cross v means v is along this direction and RB is along this direction. R cross v means like this is the direction of r cross v. Okay, if you keep a screw here and rotate in this direction, you will see that the screw will advance in this direction. That means if you take the axis here, x axis, y axis, z axis, your screw will be advancing along this direction, coming along this direction. That is a resultant of r cross v. There is nothing but z direction. If you look at this picture, the z direction is this z direction. Fine. Therefore, this z direction we can denote like a k cap, because we already mentioned the velocity is along x direction, that is denoted by I cap. Okay, this is k cap direction, that is our LB. Therefore, here I can write this is a k cap. Fine. This is the angular momentum of the particle. Now, I can further simplify. See here in this picture, if you calculate sine theta, that is opposite side L divided by hypotenuse RB, then the RB sine theta one can write L. Then if you come back here, here we have RB, here sine theta. Therefore, M V RB sine theta K can be replaced as MV, that is, replace this RB sine theta by this L. This is L and K cap. Fine. Therefore, I can write our LB, the angular momentum of the sliding block, is MVL K cap. Let me put this is equation number 1. Now we consider a case that our block is sliding freely. That is, sliding freely means without friction. No friction is acting on our block. That block is moving freely. Then let me write, if we consider if the block is sliding freely, that is without friction. Later we will discuss with friction what will happen to the angular momentum and the torque. Okay, here now first we will deal with if the block is sliding without friction. Without friction means if any object, if that is moving with an initial velocity v, if there is no friction acting on this body, that it will move without any change in the velocity, because there is no opposing force. If friction is present, then the velocity will decrease. Okay. If no external force is acting on the system, the speed of that object will be constant. Therefore, the speed v is equal to constant, or the velocity v is equal to constant. Now, then you come to this equation number 1. Here the angular momentum L depends on the mass, the velocity and the length L. That L, you know that L is nothing but this one. That is constant. But direction K, that is also constant. Therefore, if V is constant, then the LB, angular momentum, is constant. Therefore, LB is also constant. Fine. Then what about the torque acting on the system? The torque is nothing but dl by dt. If L is constant, then this will be 0. Time derivative of a constant is 0. Okay. Now I consider the case that when there is a friction, here we consider without a friction. Now consider a friction. That is, now the block, consider how the block slows down because of friction. Okay, if any friction is there, then our block of mass m, if that is moving with the velocity v in this direction, if a friction is there in the opposite direction, frictional force, that will opposes the motion of this object, therefore the velocity decreases. Okay, that frictional force is F. One can say that if this is the x direction, x cap, the frictional force F is nothing but magnitude of the force into I cap, but it is in the negative direction. Let us calculate what is the torque acting on the system. Before that, let me write that friction F is equal to minus Fi. The torque acting on the system, torque acting on the block about the origin B, because we are calculating the angular momentum and the torque about this origin B. Okay, fine. Then dou B is nothing but R cross F. Here the force F is a frictional force. Fine. Then let me write what are the direction of RB and F. Here the F is along this direction and RB vector, that is along this direction. We have already discussed the direction of the RB. This is our RB. Okay, fine. Next we have to calculate what is the direction of this R cross F. R cross F, that is, if you place a screw here and rotate along this clockwise direction, then you can see that the screw advances, or that screw goes along this direction. This direction is nothing but minus Z direction, or we can say this is minus K cap direction, because we have taken this is a X, this is a Y, and this is a Z. Earlier we have seen that this LB, that is along K cap direction, that is Z direction, is Z, and now here our torque, that is along this advances along this Z direction, that is Z is minus K. This we have taken plus K, then this is minus K cap direction. Therefore here I can write RBF sine theta K cap with the minus sign. Okay, fine. And one more thing, this RB sine theta, that is, I will write this is a RB sine theta K cap. This RB sine theta, that we have seen that there is nothing but L. Dou B therefore is equal to minus FL K cap. Let me put this is equation number 2. Fine. Now we have calculated dou B and angular momentum L. Next we will verify the relation, that is, we have to show that this dou B is equal to minus FL K cap can be obtained by finding out the time derivative of this LB. Fine. That is our aim. To show that one, let us take the case that when the friction is present. When the friction is present, the block slows down. Okay. The block slows down means, what about the angular momentum? The angular momentum LB that we obtained was mvlk cap. If this V decreases, velocity decreases because of the friction, angular momentum will decreases. That is, this angular momentum is a vector quantity. The magnitude decreases when the velocity decreases, but the direction of the angular momentum will not change. I will show you the picture. The angular momentum is along the Z direction, this one, but when the velocity decreases, there will be a change in the angular momentum because of the change in the velocity. Therefore, let me note down that though the magnitude of the angular momentum changes, the direction of the LB remains along the positive z direction, but its magnitude decreases. Okay, therefore the change in delta, the change in the angular momentum, that is delta LB, that points in the negative z direction. Fine. Therefore, the direction of delta LB, that is, see, the direction of delta L is back direction. We have seen that the torque is acting along the same direction. See this torque is acting along the minus k direction. This was the direction of the torque. The change in angular momentum direction is also along the same direction. I will show you that picture. Here you can see that the dou B is along this direction and our delta L also along the same direction. Okay, therefore I can write direction of LB is equal to direction of tau B. Fine. Then what is this tau? Tau is nothing but dl by dt. Everybody knows. How we can write the dl by dt? This is nothing but limit delta t tends to 0, delta L by delta t. Here we have delta L. What is delta L? Delta L is equal to, we have mLv k cap, but that is the expression for the L. The change in angular momentum occurs because of the change in the velocity. Therefore, this should be written as delta V k cap. Okay. Now differentiate with respect to time or divided by delta t. Delta L by delta t is equal to mL delta V by delta t k cap. To get this equation, we have to apply the limit delta 0, limit delta t tends to 0, delta L divided by delta t is equal to mL limit delta t tends to 0, delta V by delta t into k cap. Fine. This quantity is nothing but dl by dt. This is ml, and this quantity is nothing but dv by dt. And if you write this is as L into m dv by dt into k cap. It is our dl by dt. This quantity is nothing but mass into acceleration, that is minus f. Here the velocity decreases, therefore the retardation force is negative. The F is equal to mdv by dt is nothing but the minus F. Okay, this is from the Newton's second law. Therefore, here dl by dt can be written as, this is angular momentum about the B point, B. Okay, angular momentum about the point B, that is equal to minus, this minus, wrote first, LF k cap. This is equation number 3. See, this term we have seen earlier. Please come back to this minus LF k cap, where we have seen, yes, the equation 2. The equation 2 is nothing but tau B. Tau B is minus FLK. That is, the right hand side is nothing but tau B. Therefore, we have verified that relation dou LB by dLB by dt is equal to minus this minus dou B is equal to minus LF is equal to dou B. Fine. Here we have to note down that the while verifying this relation, the dou and LB depend on the choice of the origin. The same origin must be used when applying the relation dou is equal to dl by dt. Actually, in this example, the angular momentum of the block changed only in magnitude and not in the direction. Okay. In the next example, there is a conical pendulum where the magnitude of the angular momentum will be constant, but its direction changes due to an applied torque. Then let us come to that example. That is the next topic in your syllabus. Torque on the conical pendulum. We met this conical pendulum earlier also. Okay. Here I will show you the picture of the conical pendulum. Here the question is this one. This is a mass m that is rotating about the point A, and we have to find out the torque acting on this mass m about the point A and also about the point B. The point B is here, and we also have to show that the relation tau is equal to dl by dt is satisfied. Okay, let me write the question first. Find torque acting on mass m about the point A and B. Okay, also show that the relation tau is equal to dl by dt is satisfied. Fine. Now let us address these questions. First, we have to calculate the torque acting about the point A. Tau is equal to Ra cross F. That is, R means this vector R that is allowed radially outward. Therefore, this we can write, this is nothing but R A R cap. Then what is this force F? That force F is the force acting on this mass m. That mass m is moving along the circular path. The force acting on this mass m is a centripetal force, because for every body to move along the circular path, there should get a centripetal force from the center. Then what is the values of this force F? That we need to find out. For this, let us resolve this T into 2. This is an angle alpha. Now you can see that this is like a N. If this angle is alpha, this angle is also alpha. This vector is T. Then our force is towards the center. Force is along this direction. If this is the center, your force is along this direction. Then this is opposite side. Then if you take the sine alpha, that is this opposite side divided by hypotenuse T, then that opposite side is nothing but your force. I will write that is the force F. That F is equal to T sine alpha. But that force is directed towards the center, because here this is centripetal force. Therefore, I have to take minus T. Therefore, here I can write this force is nothing but minus T sine alpha. What about direction? Direction is towards the center, towards along the R, towards the center. Therefore, this F can be written as minus T sine alpha R cap. Fine. The next step, I can write this relation as RA R cross, R cap into cross, minus T sine alpha R cap. Here minus T RA sine alpha R cap cross R cap. R cap cross r cap means it is 0. A cross A is equal to 0. Therefore, the torque about the point A is equal to 0. Fine. That is, if torque is 0, then one can write tau is equal to dL by dLA by dt. That equal to 0. That means this LA is a constant. Shows that LA is constant. Fine. The torque measured from the point A, that is found to be 0. Now we take the origin as a B. First we took the origin as A and we found that torque acting on this object is 0. Now we take the origin as a B. Then let us calculate what is the torque acting on this mass M. Fine. Now take origin at B. Then torque tau B, we can write tau B, that is equal to RB cross FA. See in this picture, our origin is at B now. We have to calculate the torque. Fine. The force, that is the force is this force, centripetal force. First let us calculate the magnitude of tau B. Okay. That is tau B magnitude is equal to RB FA sin theta. What is this angle theta? The theta is nothing but this angle. Angle between RB, this is RB, and the force F. Okay, this is RB, this is force FA. The angle between them, that is this angle, is theta. Angle between RB and FA. See, if you refer this figure, here we have alpha angle, theta angle. This angle is 90 degree. Then let me draw the triangle like this one. This is alpha, this is theta, this is 90 degree. Then alpha plus 90 plus theta is equal to 180 degree. Alpha plus theta is equal to 90 degree. Theta is equal to 90 degree minus alpha. Therefore, instead of this theta, I can substitute 90 minus alpha. This is RB FA sin 90 minus alpha. Fine. You can apply sin A minus B relation. RB FA sin A cos B minus cos A sin B. This term went to 0. Then we have RB FA cos alpha. This is tau B magnitude without a vector sign. And just now we have seen that this force FA, that force, this force was FA. That force is nothing but minus T sin alpha r cap. Minus T sin alpha magnitude. Direction is r cap. Fine. What about this RB? If you look at this picture, this RB is nothing but length of the conical pendulum. This is L. Therefore, I can write tau B is equal to L T. Actually, we are interested in the magnitude. Therefore, no need to consider this minus sign. Sin alpha cos alpha. Okay. Or I can rearrange the term L sine alpha t cos alpha. Why I have written t cos alpha? See, if you see this picture, the cos alpha we can find out by drawing the free body diagram. See here, our mass is m here, and the forces acting on this body is downward mg. What about the upward direction? That is, the upward direction means this side, or one can say that this direction. If you look at here, this angle is alpha, this is t, and this side will be t cos alpha, and your mass m is here. The downward force acting is mg. There is no acceleration along this direction. This direction is nothing but z. This direction is z. No vertical movement of this body. Therefore, the acceleration is 0. Okay. Therefore, I can write this is nothing but t cos alpha. Then from this one can write the equation, that is t cos alpha minus mg is equal to 0. Okay, that is here t cos alpha minus mg is equal to 0. T cos alpha is equal to mg. That is my interest. This is replaced by mg. This will be L sine alpha into mg, or simply we can write this is a mgl sine alpha. This is nothing but the magnitude of the torque without direction. Now let us calculate the direction of the torque separately. Okay, so far we were calculating the magnitude of the torque. Now we are calculating the direction of the torque. Then the equation is tau b with vector sign RB cross FA. RB we know the direction, R cap, RB cap we can write, cross the force. Actually, our bob of mass m was moving along the circular. So we have to calculate the dou p. For this we must know what is direction of RB. RB is coming from here, therefore this is the direction of RB. Next, the force FA, whose direction is along this direction, FA. Now R cross F is nothing but this one, clockwise direction, rotation. Place a screw here and rotate along this direction. You will see that screw will advance along this direction. Then the force FA, its direction is actually along minus R cap, that is along this direction. This was our radius vector, and its direction is this is minus R cap direction. This R cross F means that is along this direction, theta. Fine. Okay, or simply you can write this is a minus R cap, or this direction instead of R cap. If you take FA, no issue, it will be equal symbol. The direction of R cross F is along this angle theta. Fine. This is a theta is the unit tangential vector in the plane of motion, theta cap. Therefore, tau b vector with its magnitude and direction we can write mgl sine alpha theta cap. This is the magnitude and direction of the torque about the point B. Fine. Here note down this theta is the unit tangential vector in the plane of motion. Fine. Now we have calculated what was our aim, to calculate the tau A, then to calculate tau B, then to calculate the relation tau is equal to dl by dt. Fine. The tau A is calculated here. Sorry, tau B is calculated here. That is the final value we obtained here. Tau B. The value of LB, because tau is equal to dl by dt. Next, our aim is to calculate the to verify the relation. Tau B is nothing but dlb by dt. Then we want to know what is LB. That LB we have already found out a few classes before. Okay, we will take that value directly here. Before that, let us write a few words here. Now we have to show that dou B is equal to dl by dt is satisfied. Fine. For this, we know the LB, angular momentum of the block of mass m. Let me write that mass is here, and from the point from the point B, that position vector is this one, and its angular momentum is this quantity. LB is equal to mLr omega, where L is this quantity. That we have already derived this expression, and here the angle is alpha. Then this distance, that is nothing but this is along the radial distance, and this is along the z direction. Therefore, this is Lz. That is, this LB now we can resolve into two components, Lr and Lz. Okay, this Lr means mLr omega. This is a cos phi. Lr is equal to mLr omega cos phi, because this is Lr is adjacent side of this angle. Its direction is r cap, because our object is the angular momentum along this direction, r cap, and this is our z direction, Lz. This is Lr direction. Next, Lz is equal to mLr omega. If you take the sine alpha, that is the opposite side, that is nothing but Lz, sine alpha z cap. Instead of z cap, we have used k cap. Therefore, here add those two terms, mLr omega cos alpha r cap plus mLr omega sine alpha k cap. Our aim is to calculate the torque from this angular momentum. That is, for this, differentiate this angular momentum with respect to time. That is, mLr omega cos alpha, everything is constant. Why this alpha is constant? If you look back to this picture, this is alpha. Our object is moving along this direction. This alpha is constant. Okay. Mass is constant. That length L is constant. Radius is constant. Then what else? The dr, we can differentiate dr by dt plus mLr omega sine alpha. The change in the z coordinate, that is constant, no change. The direction does not change. Therefore, this is 0. Okay. Therefore, this quantity is 0. Why? When this simple pendulum, this bob rotates, the angular momentum is along z direction. Z direction. That will not change. That is, z is direction is constant. That is not changing with respect to the time. When the object moves, then the only parameter changing is the direction of the radial vector. See here, our object is here, then the radial vector is this one. When the object reaches here, the radial vector direction changes. When here direction changes, the radial vector, that is that radial vector direction changes with respect to time. Therefore this is not zero. This quantity is not zero. Then what else we have? We have this quantity. That quantity is nothing but omega theta cap. That is dr cap by dt is equal to omega theta cap. I had given an assignment at the beginning of this course where you can see that this relation dLb by dt is equal to time derivative of LB mLr omega cos alpha omega theta cap. Write omega together. mLr omega square cos alpha theta cap. What is this mr omega square? mr omega square. Okay, next step I will write those terms together. mr omega square L cos alpha theta cap. This quantity, that is nothing but the radial force mvr. V is equal to r omega. Then you will get the radial force. See, F is equal to mv square by r. Expression for the centripetal force. Omega is equal to v by r, or v is equal to omega r. You substitute here, then you will get m r omega square. That is nothing but the centripetal force. In this case, there is a force towards the center. We call that force is Fa. That is a radial force. That radial force, we obtained a relation that was T sine alpha. Okay. Therefore, I can write this dLb by dt like this one. T sine alpha. Here T sine alpha. L cos alpha theta cap. Fine. That is, if I rearrange the term, I can write this is a L sine alpha T cos alpha theta cap. What about this T cos alpha? We have seen that T cos alpha minus mg equal to 0. T cos alpha is nothing but mg. Therefore, this L sine alpha is replaced by mg. There is a theta cap also. Next, dLb by dt, I will write in this fashion mgl sine alpha theta cap. Let me write this is a equation number 2 or 3. We have calculated the time derivative of the angular momentum. Let us check whether we have any value to substitute this RHS. mgl, yeah, mgl sine alpha. Here we have, yes, see here, tau b is equal to mgl sine alpha theta. That is the angular momentum of the, torque of the conical pendulum. This is nothing but tau p. This is equation 1. Therefore, let me write, compare equation 2 and 1. One can write dLb by dt is equal to tau p. We have this, we verified the relation. Now we answered the 3 questions. First we calculated the torque about the point A, then torque about the point B. Then we verified the relation tau is equal to dL by dt. Fine. Next, there are certain systems in which the gravity exerts torque. That is a next topic in your syllabus is torque due to gravity. Like you know the systems like a pendulum. When the pendulum oscillates like this, the external force acting on this bob of mass m is gravitational force. Then what is the torque exerted by this gravitational force on this bob of mass m? Okay. Another example. The gravity exerts torque on a system. That is a second example. Child is top, pambaram. Okay. That is here. When the top rotates, after some time it will stop because there is a gravitational force acting on this top. Here, the torque acting on the body about any point due to gravity is the cross product of the position vector. Okay, that is, let me write, if this is a body and we have to calculate the torque due to the gravity of this body, if this is a point A and if this is the center of mass point and this is the position vector r, then the gravitational force acting on this body is, we know that W, that is m into g. Everybody know the expression for the torque is tau is equal to r cross f, and here the r is the position vector to the center of mass, that is r, cross the weight is nothing but the gravitational force, that is nothing but the weight. This is a torque due to gravity. Fine. Then the torque due to gravity, we can write these few words. That is the torque acting on a body about any point due to gravity is the cross product of the position vector to the center of mass, that is r, and the weight of the body, that is w. Torque. Okay, the torque acting on a body about any point due to gravity is the cross product of position vector to the center of mass, that is r, and weight of the body, w. This torque can be written as r cross w. Actually, I have not proved here. Please do a homework. Its solution is given in the Kleppner textbook. That is, you do this assignment, do this homework. That is, show that the torque exerted by the gravity on a body having weight w is r cross w, where r is the vector from the point to the center of mass. Okay, while submitting the lecture note, please write the solution of this question. Okay, thank you very much.